back to the next lecture in mathematical modeling. We had already finished a brief look at conservation laws, notation and mathematical preliminaries, and we started off with the governing equations of fluid flow. We had derived continuity equation and Cauchy equation. Today we would focus on the specialized form of momentum equation for a Newtonian fluid, which we call Navier-Stokes equations. Before we proceed further, let us see what we did in last lecture. In the previous lecture, we derived the integral form of momentum equation starting from Newton's second law of motion for an arbitrary control volume, and thereafter we invoked Gauss divergence theorem and obtained a differential form of momentum equation starting from this integral equation. Now in today's lecture we would focus on obtaining an appropriate form for what we call Newtonian fluids. That is our popular Navier-Stokes equations, which form the backbone of practical CFD analysis. This is outline of today's lecture. We would finish the unfinished business of previous class. We would derive the Cauchy equation using a differential control volume. Then we would have a look at what we mean by constitutive relations, and thereafter we would derive Navier-Stokes equations. We will also have a look at few simplified forms, notably the Euler's equation. Now this is what we did yesterday, that we derived the differential form of momentum equation starting from the integral form, and this was the first one was our so called conservative form given by del rho v by del t plus divergence of rho vv is equal to divergence of tau plus rho into b, where tau is stress tensor, b with the body force, and this equation is popularly referred to as Cauchy equation of motion. Same equation we can write in Cartesian component form using tensor notation: del of rho vi over del t plus del of del xj rho vi vj is equal to del tau ij by del xj plus rho bi. So this represents the momentum equation or Cauchy equation for ith component of velocity. So we have got a total of 3 components for 3-dimensional space. Now today we would focus on obtaining the same equation in differential form using a differential control volume in Cartesian coordinates. So to derive this equation, and let us first have a brief look at the conventions used for the stress components. Conventions for the stress components. For the sake of clarity, let us draw a 2-dimensional element this is x direction, this is y direction, and let us identify the stress components which will work on the small area element. The first one on the right face, which we would call this as your positive x plane, because normal to this area element points in positive x direction. So the stress component here is referred to as tau xx, the normal component on this face, and it would be considered to be positive if it is aligned in x direction. Similarly, we have a shear component on this surface directed in y direction, let us call it tau xy. Similarly, on the negative x face, tau xx, and we can draw these stress components on y planes. This tau yy, this is normal component, tau yx, tau xy, and this is tau yx. So, what is the convention which we have adopted? Suppose we use symbol tau x1 x2, this denotes a stress component on x1 plane directed in x2 direction. For example, if we say this tau xy, this denotes shear component on x plane directed along y direction. So, this is about the subscript notation which we use to identify different components. The next one is, when will these components be considered positive? Is stress components are considered positive if there are two possibilities, that if they are along positive coordinate axis on positive planes, that is the planes whose normal are in positive axis direction, and B on negative planes aligned along negative axis. So, this is why if you look at the way we had drawn this tau yy on our y plane, this is a positive sense of the stress component, and it is drawn, it is pointing in negative y direction. The same holds for the shear component tau yx on this negative y plane, it will be considered positive if it is aligned in negative x direction. Now, let us move on to our momentum equation. And we were going to derive it in Cartesian components. First, let us find out the forces acting on a differential element. So, let us draw a simple differential volume in 3-dimensional space. Let's label the axis properly x, y and z. So, origin. For the sake of clarity, now let us identify the stress components which are aligned in x direction. Each side of this element, it has got extent dx in x direction, dy in y direction and dz in z direction. Now, let us identify the stress components first on the positive x plane, which will act on the centroid of this face. On negative x face, let us call this as tau x x. Now, with reference to the origin, this tau x x component acting on the positive x face, that can be denoted by Taylor series expansion. This can be written as tau x x plus del tau x x over del x dx. And if you want to find out the force on these faces, we need to multiply by the respective areas. We will do that later. Now, what are the shear components which would work along x direction? Let us focus on positive y plane. So, we would have one shear component which will be along positive x direction. Similarly, on negative y face, it would be aligned in negative x direction. So, this component is tau y x, and this tau y x component on positive y face, this would be given by tau y x plus del tau y x over del y dy. Similarly, we can identify the shear components which work along x direction on z faces. On positive z face, it will act in positive x direction, and on negative z face, it will act in negative x direction. This is tau z x. On the positive z face, we can represent in terms of Taylor series expansion as tau z x plus del tau z x over del z dz. What would be the body force in x direction? So, this mass of this differential element dm, this is rho dx dy dz. So, if you denote our body force by symbol B, the body force per unit mass then body force in x direction, let us call that as dfbx. This will be simply dm times bx or rho bx dx dy and dz. Next, let us find out the surface forces. The surface force in x direction, let us call this as dfb Sx. So, let us see, let us find out all the components. First, let us write the components due to the normal stress tau x x in x direction. So, on positive x phase we have got this tau x x plus del tau x x divided by del x dx multiplied by that area dy dz. The force acting on the negative x phase due to this normal component, that is in negative x direction, and this given by minus tau x x dy dz. Next, the force due to the shear component, first the ones on the y plane. So, the negative y plane we have got is minus tau y x dx dz plus the component which is acting on the positive y plane, that is tau y x plus del tau y x over del y dy into dx dz, and the last term would be the contribution coming from the shear stress on z planes. So, on the negative z plane we have got minus tau zx dx dy, and on positive z plane this is our stress component multiplied by area and we get the force. So, tau zx plus del tau zx over del z dz dx dy. So, we can clearly say the first one, this component, this cancels by this, tau yx gets cancelled, similarly here tau zx gets cancelled with tau zz, and we get a very simplified form for this dfsx, and this is given by del tau xx over del x plus del tau yx over del y plus del tau zx over del z dx dy dz. So, finding the resultant force in x direction now very simple. So, thus a resultant force in x direction dfx, which is sum of surface and body forces, that will become rho bx plus del tau xx over del x plus del tau yx over del y plus del tau zx over del z dx dy dz. Now, we can invoke Newton's second law, and we have got one form of Newton's second law which says F is equal to ma. See, if we apply this particular form and apply it to our small differential element, so what do we get? dm times ax, which is equivalent to rho dx dy dz into d of u by dt. du by dt is material derivative of the x component, which gives us the acceleration in x direction. This would be equal to d of fx which we have derived in previously. If we substitute these two equations and simplify, we get rho times du by dt is equal to rho bx plus del tau xx over del x plus del tau yx over del y plus del tau zx over del z. So, this is the momentum equation derived in x direction or for x velocity component. We can repeat the same exercise and we can obtain these differential equations for two other velocity components as well, and you can easily identify that what we have derived just now, this represents non-conservative form of momentum equation. So, to derive the conservative form of momentum equation, we have already found out what are the forces acting on this differential element. Now, let us find out the rate of momentum efflux, and once again we would focus only on momentum exchanges in x direction, and to simplify the visual representation, let us first take a two dimensional element, or rather let us have a look along x y plane, and let us see the momentum efflux or influx which is coming from different areas. At the centroid of the negative x plane, we have the velocity component given by u and rate of mass flux that will be given by rho times u. On the positive x face, here this u has to be obtained from Taylor series expansion, that u x plus delta x, and similarly this rho u, this has to be obtained again in terms of Taylor series expansion. Same thing about the y velocity components. This is v velocity component, rho v, which will represent an influx with this velocity. On the positive y plane, we will have the fluid going out with the velocity v, small v. Now, these quantities must be evaluated at y plus dy. Now, if you look at these y planes, the contribution of these velocities in x direction momentum efflux would not come directly from this, but instead what is the momentum transfer along x direction, that would be given by finding out what would be the x velocity components at these locations. So, with reference to the centroidal planes, at negative y plane we have the x velocity which should be evaluated at y minus dy by 2, and the top face it has to be evaluated at plus dy by 2. Okay, now let us find out these momentum exchanges arising from each velocity component. So, momentum efflux in x direction, number 1 due to velocity component u which is in x direction. Let us call this as Pxx. So, what is the momentum going out? It is rho u at x plus dx multiplied by the area dy dz, that gives us the mass flow rate multiplied by the velocity here, which is evaluated at x dx, minus the incoming momentum, which would be given by rho u dy dz multiplied by u. Expand the first term on the right hand side. So, we will have rho u plus del of rho u over del x dx multiplied by dy dz into u plus del u by del x dx minus rho u dy dz to u. Let us carry out the multiplications and find out which terms would we have to retain. So, first multiplying two terms on the first side. So, we get rho u u dy dz plus u times del over del x of rho u dx dy dz plus rho into u times del u by del x dx dy dz plus del of rho u over del x del u by del x dx squared dy dz minus rho u u dx dy dz. So, last term gets cancelled by the first term, and let us take out dx dy dz outside. So, we are left with u times del of rho u over del x plus rho u times del u over del x plus del of rho u del x del u by del x multiplied by dx, and this whole thing gets multiplied by the differential volume dx dy dz. First two terms, like these two terms, can be combined as a single derivative by using chain rule. So, this can be written as del of rho u u by del x plus del of rho u over del x del u by del x dx dx dy dz. Now, let us have a look at the second term in the bracket, that is this particular term. It is being multiplied by the differential area element dx, which is infinitesimally small quantity. So, compared to the first term, this can be easily neglected. So, we can approximate Px x as del of rho u u by del x dx dy dz. We can repeat the similar exercise, and we can find out that momentum efflux in x direction due to velocity component V, if we call this as Pyx, this can be obtained as del of rho uv over del y dx dy dz, and similarly we can obtain the contribution of z velocity component. Now, let us combine these together. So, thus this rate of momentum efflux in x direction let us call it small p x out. This is sum of three terms which I have done earlier, p x x plus p y x plus p z x, p dot x out. This can be written as del x of rho uu plus partial derivative with respect to y of rho uv plus partial derivative with respect to z of rho uz. So, now what is the rate of momentum change in x direction for this differential element? Rate of change of momentum in x direction dpx by dt. We can invoke this Reynolds transport theorem. So, this will be given by del of px over del t plus p dot x out. Now, what is px? Px is nothing but dm multiplied by u, which is rho dx dy dz. So, therefore, dpx by dt is del of rho u by del t plus del x of rho uu del y of rho uv plus del z of rho uz multiplied by dx dy dz. Now, from Newton's second law, this dpx by dt, this would be equal to the resultant force in x direction, which we have denoted by dFrx, which we have derived earlier. Let us substitute the expressions of both of them. So, on the left hand side we get del of rho u over del t, del x of rho uu, del y of rho uv plus del z of rho uz multiplied by dx dy dz. This is equal to our first term rho b x plus del tau x x over del x plus del tau y x over del y plus del tau y z over del z dx dy dz. We can divide by this volume of differential element dx dy dz, and thereby we get this x momentum equation del rho u by del t plus del of rho u by del x plus del of rho u v over del y plus del of rho u z over del z this should be equal to rho b x plus del tau x x over del x plus del tau y x over del y plus del tau y z z x over del z. And this is precisely the expanded form of Cauchy's equation in x direction. So, this is our Cauchy's equation in conservative form. Okay, so we have now just derived only one component or equation for only one momentum component. The similar equations can be derived for the momentum equations in other two directions. The whole purpose of doing this exercise was that how we can obtain the desired governing equations is starting from the first principles. As an exercise, you can try and derive this momentum equation in planar polar coordinates, or let us say cylindrical polar coordinates. So, derive the momentum equation for a 2D case using a polar differential element, that is using r theta coordinates. So, once we have done this exercise, this will give us the confidence that for a specific application we should be able to derive the governing equations ourselves, which is the first step in our numerical simulation. Now, let us get back to the formal form of these equations. So, what we had on the left hand side, the first term in momentum equation, that is what we call temporal derivative, which was in terms of the density rho and velocity components, velocity vector v. The second component is what we call the convective term, which again involves rho and v. On the right hand side we have got two terms. The first one is divergence of tau, where tau is a second order stress tensor, and the last term is in terms of rho into b, b is our body force. In a given problem, we have to obtain what would the density be. We would like to find out what are the velocity components at each point in the flow domain. B would normally be specified, okay. But how about tau? If you combine a Cauchy equation with our continuity equation gives us an equation for transport of density, so that is one equation, and these equations represent the Cauchy equation of motion represents a set of 3 equations. So we have got 4 equations in terms of how many unknowns, density is 1, 3 components of velocity, that makes it 4, and we have got 9 components of this stress tensor. So this system of equations is still not closed. We have got more number of unknowns than the number of equations, and that brings us to the topic of what we call constitutive relations. That is, we have got 9 additional unknowns which are components of stress tensor in our momentum equation. Now these components, these 9 unknowns, they must be modeled or they must be expressed in terms of our primary unknowns, which are velocity, pressure and density. So we need to use what we call constitutive models for relating the stress tensor to the velocity components. In fact, we will try to relate this stress tensor to the rate of stress or rate of strain tensor. So a relationship between stress tensor and rate of strain tensor is what we would call a constitutive relation. And the simplest model, which is proposed long time ago, was that by Newton. It's a linear relation between the stress and strain rate, and this model is valid for what we call Newtonian or Stokesian fluids. Why do we call these fluids as Stokesian? That would become clearer when we look at the formal derivation of our Navier-Stokes equations. Now let us have a look at a general constitutive relation. Now when we want to relate the stress tensor to the strain rate tensor, we can write a general functional form. Tau is equal to a function of the strain rate tensor S, the first derivative of S, the second derivative with respect to time of S, and so on, where this strain rate tensor S is given as 1/2 gradient of V plus gradient of V transpose. Now you might wonder why we have just taken the strain rate tensor and why not rotation component. Normally what we would think that in a moving fluid the stress arises due to velocity gradients, but if you look carefully, the rigid body rotations which are represented by the rotation tensor, they do not contribute to the stress generation, and that is why the stress is normally related only to the strain rate tensor. To give a simple example of this particular functional form, for a second order fluid with memory, which is typically referred to as viscoelastic fluid, tau could be given as minus p into I, where this capital I represents Kronecker delta or identity matrix, which is a second order tensor with 9 components, plus alpha 1 times S plus alpha 2 times S square plus alpha 3 times S dot. Now here these P, alpha 1, alpha 2 and alpha 3, these would depend on the thermodynamic state of the fluid. For Newtonian fluid, where we have a simple linear relationship between stress and the rate of strain, we get a fairly simplified relationship. How do we obtain this relation? This tau is equal to minus pi plus lambda times divergence of V into I plus twice mu times S. We will find it out. How do we say that if we assume a linear variation, we would get this particular component? And the term which we, if you look carefully, we have got tau is equal to minus p into I, from where this p crops up. What is justification of having this scalar term in a momentum equation? So now let us have a look at that justification. So this is constitutive relation for a Newtonian fluid. What do you mean by Newtonian fluid here? We would focus only on the fluids for which stress and strain rate relationship is linear. You will not consider the so called non-Newtonian fluids for which the stress strain relationship is non-linear. Now, if we are dealing with this isotropic fluid, in an isotropic fluid medium, whatever constitutive relation we come up with, that should satisfy few constants. So, let us consider this two specific cases. The first case is fluid at rest. When the fluid is at rest, what do we say in this case? That stresses in the fluid are independent of direction, of orientation of a specific plane. In fact, this is nothing but what we call as Pascal's law. Okay, which says that in a static fluid, we have an isotropic state of stress, which is the same or which is or it can be reworded what we say that look, we have got a single scalar component or a scalar quantity which describes the state of stress in a static fluid, that is stress state is given by a scalar quantity. Which is called pressure. So, if that were the case for static fluid, we must represent the stress tensor as minus p times capital I, where I is your Kronecker delta or Irente matrix, or in component forms we can write as tau Ij is equal to minus p times delta Ij. Now, the presence of negative sign before p, that is due to the convention which you follow for p and tau. The normal components of tau are considered positive in tension, whereas pressure P is considered positive in compression. So, that is the reason why we need a negative sign. That is why we need this negative sign on RHS. So, we have seen the state of stress, how we are going to represent for a static fluid. The remaining part, that what happens for fluid in motion. Here we will have additional stresses, generated due to viscous action. Okay. So, we are going to stop here in this lecture, and what would be the additional forms or additional terms which we need to add to obtain the stress tensor for a moving fluid is what we will look at in the next lecture.